Okay, so one of my students suggested that I go through some KC exam questions. So I've chosen an OCR Chemistry A June 2012 question and a June 2014 question. It doesn't matter that they're older exam questions, they are both very good questions. So let's start with the June 2012 question. And here you go. Now I'm hoping that you're going to have a look at the question, pause the video, have a go at the question, and then restart the video in order to see if you've got the right answer. Okay, so let's start with a KC expression. So KC equals, remember that it is square brackets and it is products, carbon dioxide, to the power of 2 times square brackets concentration of nitrogen over the reactants. So that's square brackets carbon monoxide again to the power of 2 times NO square brackets again to the power of 2. Be careful with your brackets, because if they're not square brackets you can lose a mark. Right, and it asks for the units of the equilibrium constant. So the units of concentration are moles per decimeter cubed. And can you see that on the top we've got to the power of 3 on the top. There are 3 concentrations. And then on the bottom we've got the units of concentration again, but can you see that we've got to the power of 4? So we can cancel out, the 3 of the concentrations can cancel out. So we're left with 1 over concentration. And I'm just going to hold the brackets around the concentration. So 1 over concentration is the same as concentration to the minus 1. And then when you bring minus 1 into the brackets, then you'll have mole to the power of minus 1. And this is timesing is what you're doing here. And it's dm cubed. But really, we shouldn't leave the units like that. We should put the positive indices first. So it's dm cubed mole to the minus 1 is the actual answer for the units. Okay, right, then the second part of the question is to determine the Kc value for this equilibrium mixture. So I'm just going to rewrite the equation. The equation is given on the start of the question, and I'm going to rewrite the equation. Now please remember, you have a go at this question as well. So press the pause button and you have a go at it as well. Just 2 CO is the equation, plus 2 NO goes to 2 CO2 plus N2. Okay, and we've got the initial, I'm just going to write I for initial moles, and I'm going to go back to the question to find out the initial moles. It says the chemist mixes 0.46 grams of CO, so I'm going to write it right there, 0.46 grams of the CO and 0.45 of the NO, and this is the initial moles. And the mixture is left to reach equilibrium. Okay, so there isn't any carbon dioxide or nitrogen initially. It's left to reach equilibrium, so I'm now going to put E for equilibrium. Remember, this is all in moles. This is moles, equilibrium moles. So the student analyzes the mixture and finds that 0.25 moles of NO remains. So 0.25 at equilibrium, 0.25 moles. Okay, now what we need to work out is the change. We've got the initial, we've got the equilibrium, and we need the change. So between initial and equilibrium, what has happened to the amount of NO in the container? So you have to subtract those two numbers. What's the difference between initial and equilibrium? So you subtract them and you see it's decreased, it's gone down by 0.2. That's the change. So therefore, what is the change going to be for the CO? Because we're trying to find, remember, we are trying to find the equilibrium amounts of each of the items so that we can find the value for Kc. So what is the change? Now you need to look at the numbers at the start, and there is 2, 2. The ratio is 2 to 2. Yeah, so it's the same ratio. So therefore, if minus 0.2 is left lost on the NO, the change is going to be the same. The change is going to be the same on the CO because it's ratio 2 to 2. So 0.46 minus 0.2 is going to be the answer, 0.26. Now let's look at the change on the product side. So how much CO2 is going to be formed? Now again, look at the ratio. They're all the same numbers. So it's going to be plus 0.2. Plus 0.2. So therefore the equilibrium amount of CO2 is going to be 0.2. Okay? And then with nitrogen, what's the change going to be with nitrogen? Okay, now I'm going to be careful here because now the ratio is 2 to 1. So the change is going to be 0.2, but it's going to be half of that. So the change is going to be 0.1. So 0.1 is going to be made. 0.1. And they are the equilibrium moles. Now, when we're writing Kc, it's not in moles though. It is in concentration. So we have to convert moles to concentration. And remember what the conversion is. Moles is concentration times volume. So concentration is moles over volume. So we need to convert each of these into concentration. So in order to do that, we need to divide by the volume. So let's go back and double check. It says the volume is 1 decimeter cubed. Okay, so that's quite nice. You divide them all by 1 to get concentration. So it's basically the same number. That's quite nice. Okay, so let's put them into the expression for Kc. So CO2, but don't forget it's squared, and then times nitrogen, that's the products, divided by the reactants, 0.26, and again it's squared, times 0.25, and again that is squared. Now so many people make a mistake on their calculator, so just be really careful putting this into your calculator. The answer, so in the question they've used 2 significant figures, so we're going to use 2 significant figures in the answer, 0.95, and we've already worked out the units, dm cubed mole to the minus 1. So I hope you got that right, and 4 marks. Okay, so let's have a look at the June 2014 question. And the first thing we need to do again is we need to write the expression for Kc. So very similar, this is the 2014 question. So Kc, it's concentration, and it's ethyne, the product, times the concentration of hydrogen to the power of 3, and then divide by the reactants, so that's methane to the power of 2. Okay, so that's the expression for Kc. I'm going to work out the units because we need those later on. So we might as well work them out now at the same time because we need them later on. So concentration to the power. Can you see what we've got? We're talking about to the power of 4 on the top, and the concentration on the bottom is to the power of 2. So we can cancel out 2 of those concentrations, and then we can bring the 2 inside the brackets. So it's mole to the squared, dm, remember we're timesing is what we're doing here, so it's dm minus 6, and that's the units, because we need those later on. Okay, so the next question, calculate the amount of moles of hydrogen in the equilibrium mixture. So I'm just going to rewrite the equation because I like to work everything from an equation. So I'm just rewriting the equation. 3 hydrogens. Okay, we've got initial, we've got equilibrium, and we're going to look at the change as well. So initial, change, and equilibrium. Okay, so let's see what information. The chemist adds methane. Well, we don't know how much methane, so initially we don't know how much methane. Okay, just put question mark. Oops. And adds to a container, so that's the volume. That's the volume, 4 decimeter cubed. The chemist heats the container, blah blah. The equilibrium mixture contains, so we know the equilibrium mixture is 9.36 times 10 to the minus 2 of methane, and the equilibrium mixture of the ethine is 0.168. This is all in moles. There's initially none of that, and there's initially none of that. Okay, so calculate the moles of hydrogen in the equilibrium mixture. And again, I hope you're pausing it and having a go at this yourself first. So the change from initial to equilibrium, the change is plus 0.168. 0.168 has been made. So what's the change here going to be from initial to an equilibrium? Well, it's going to be plus 1.68, but the ratio is 1 to 3, so we need to times it by 3. So overall the equilibrium, so 0.168 times 3, and that's going to give us an answer of 0.504. This is in moles, and that's the equilibrium amount of hydrogen. Okay, 0.504 moles. Right, to calculate Kc. So to calculate Kc, we need concentration. Yeah, so remember, moles equals concentration times volume. Therefore, concentration is moles divided by volume. So we have to turn these figures here at the bottom. Let's do a different colour. We need to turn that equilibrium, equilibrium, and equilibrium moles. We need to turn those into concentration. So we need to divide by 4. So what have we got? Let's have a look. So on the top, we're going to have the ethine, which is 0.168. That's the equilibrium moles of ethine. We're going to divide it by 4 to turn it into concentration, and then we've got to, we don't need to square it, that's fine. Okay, that's ethine. Then hydrogen, we've got the equilibrium moles of hydrogen, which we've just worked out, divided by 4 to turn it into concentration, and then we're going to need to cube that. And then on the bottom, we've got the equilibrium moles of methane, 9.36 times 10 to the minus 2, divide by 4, and we're going to square that one. Now be very careful putting this into your calculator. It also says give your answer to 3 significant figures, and the answer should come out as 0.153. And we've already worked out the units because we did that a moment ago. And there are the units. Okay. Right, the next question. Calculate the moles of methane that the chemist originally added to the container. So the moles of methane that the chemist originally added to the container. So let's just go back. So what we're trying to find is the moles of methane that the chemist originally added to the container. Okay, so I'm just going to redraw that part there so we can see clearly what's going on. And I've got lots of space here, so I'm going to do it at the bottom. So we've got 2 methanes. I'm just going to rewrite the equation first. We've got the ethine, and we've got 3 hydrogen. We've got the initial moles, which we don't know. That's what we don't know. And we've got initially none of those. We've got the equilibrium moles, which we know to be 9.36 times 10 what was it, 10 to the minus 2. We've got the equilibrium moles of ethine, which we know, 168, and we've also worked out the equilibrium moles of hydrogen. Okay, and the change. So we know that the change is plus 0.168. The change here is plus 0.168 times 3, because there's 3 of them. So the change here must be minus, because if it's made on one side, it's used up on the other side, minus 0.168. But there's a 2, so we need to go times by 2. So this moles of methane, the moles of methane, this is the, sorry, the equilibrium, no, not equilibrium, it's not equilibrium, the initial moles of methane. The initial moles of methane minus 0.168 times 2 is going to equal the equilibrium moles of methane. That's the equilibrium moles. And you rearrange that equation, and your answer we should use 3 significant figures again, because that's what they've used in the question. 0.430, okay, is your answer. Right, and the last part of this question, part C, so let's have a look through. It's the same equation. The chemist, part C, the chemist repeats the experiment, makes one change. Complete the table to show the predicted effect. You can only use the words greater, smaller, or same. So let's start with the container is heated. So the temperature is increased. Temperature increased favors the endothermic reaction. You can see that the reaction is endothermic. So increase in temperature is going to, Le Chatelier's principle, is going to move the position of equilibrium to the right. Therefore, the value for Kc is going to be greater, because you're moving to the right. The equilibrium amount of the ethine is also going to be greater, because you're moving, the position of equilibrium is moving to the right. And the rate, increased temperature, increases the rate of reaction, so the rate will be faster too, greater. Right, the next one, if you use a smaller container. So by using a smaller container, what you're saying is you're increasing the pressure. Now, increasing the pressure does not affect Kc. Yeah, Kc does not change when you increase the pressure, so Kc will stay the same. But the position of equilibrium will move. Increased pressure favors the side with fewer molecules. Favors the side with fewer molecules. So therefore, there are 2 molecules here, and in total there are 4 molecules here. So on the right hand side. So increased pressure will move the equilibrium to the left. So what will happen to the equilibrium amount of ethine? It will get smaller, because the position of equilibrium will move to the left with increase in pressure favouring the side with fewer molecules. The rate, because you are increasing the pressure, the rate will be greater as well. Okay, and then finally a catalyst. A catalyst is not going to affect Kc. Only temperature changes Kc. It will not affect the equilibrium amount, you just get there quicker. So the reaction will be faster, will be greater. Right, the last part of this question, in the manufacture of ethine, hydrogen is also produced. State 2 other large-scale uses of hydrogen. So you could have the manufacture of ammonia, if I spelled that right, the manufacture of ammonia, the Haber or Haber process, You could have something that you studied when you did alkenes, is the manufacture of margarine. The manufacture of margarine. And this is where you take the vegetable oil, which is a long chain alkene, you add hydrogen and hydrogenation, and you form a long chain alkane. You could have fuel cells. There are various answers you could have there. Right, I hope that's helped you. There's other videos you can look at for KC and KP2. Thank you. Bye.